We are now at the last video for the construction of the real numbers, and we are finally at the point where we can prove the thing that we were trying to prove from the very beginning. We're going to prove that the real numbers satisfy the completeness axiom. So before watching this video, I would encourage you to work on the first problem in the class activities. The reason why is that's where you're going to construct the Cauchy sequence that represents the number that turns out to be the supremum of our bounded above set. However, I should say, while we assume that you have constructed that sequence, we're going to show you all the properties that you need to understand the proof. So you don't actually have to know exactly what the sequence is, but it's helpful to know in general so that you can sort of justify what we're doing in this proof. Anyway, what we're definitely going to do in this video is we're going to start with a bounded above set of real numbers, call it S, and then we're going to describe the important properties of that sequence from the class activities that we'll need to prove that that is the supremum. We're going to take a little pause and resolve some notation ambiguities. We're going to have to, for reasons that I'll describe in a little bit, think of a rational number simultaneously as both as a regular old rational number and also as a real number that is represented by a Cauchy sequence. And then we'll finally give a proof that the real number represented by that sequence from the in-class activities is actually the supremum of our arbitrary bounded above set. All right, so we're going to start with assuming that we have some arbitrary set S that is bounded above, and we're going to show that S has a supremum, and that will give us the completeness axiom. So from the activities, you constructed, or I hope you will construct, the sequence of rational numbers, we call them x1, x2, x3, that have the following properties. So first of all, if we fix the natural number n and just look at the constant sequence where all the terms are xn, that is an upper bound of the set S. If we take the constant sequence where we again are fixing the natural number n, we take the, now all the terms are xn minus 1 over n, that one is not an upper bound of S. And finally, the sequence, the regular sequence x1, x2, x3, x4 that represent our real number, that is a decreasing sequence. We definitely proved all those in number 1 of the activities, or you will prove those. Our claim is that x, which is the number that is represented by that sequence, is the supremum of S. But of course, I said sequence, I didn't say Cauchy sequence. We haven't quite proven that that is a Cauchy sequence. So that is one detail that we're going to have to take care of. So, but before we do that, I want to talk a little bit about notation. What do we mean by the sequence when I just write bracket xn, right? Well, ordinarily, we think of that as the n can take on any natural number value, so you get x1, x2, x3, x4. That's what we used to mean. But if you look at some of the sequence from the previous slide, we were really interested in letting n just be constant and looking at the sequence that just consisted of the single number repeated xn, xn, xn. And if I just write bracket xn, it's not clear which one of those I mean. So one of the things I want to do is to resolve this ambiguity, and this is how I'm going to do it. So if I write just bracket xn, that always means what it's always meant to us. It's always the sequence x1, x2, x3, etc. So that is not going to change at all. So that is just our Cauchy sequence representing x, which again is hopefully going to be our supremum for S when we're done with this proof. Now, if at some point I want to fix the subscript and just refer to the real number that's represented by the constant Cauchy sequence xn, 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 etc., then I'm just going to call it xn. So I'm going to call it xn, and I'm going to assume, again, every real number has lots of ways that you can have a Cauchy sequence represented. I'm assuming that the representative that we're going to refer to is the constant sequence that just has xn as the terms. So when I write down the number xn, it will represent, depending on the context, both just the regular old rational number xn, which is again could be thought of as a term in the sequence x1, x2, x3, right? Those are all just ordinary rational numbers, as well as the real number who is represented by the sequence xn, 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 etc. I will try to make it very clear when I'm thinking of xn as a rational number and when I'm thinking of it as a real number. Okay, so we're not quite to the point where we've proven our x to be a real number. We need to first show that our sequence x1, x2, x3, etc., we got to show that that is a Cauchy sequence. Believe it or not, we're actually more than halfway there, right? We know it is a decreasing sequence. We just have to show that it's bounded, because any bounded decreasing sequence is a Cauchy sequence. So we know it's decreasing, and that means it's bounded above by its first term. So x1 is an upper bound, so our sequence is bounded above. Now we just have to show that it's bounded below. But that's actually not as difficult as it sounds, because remember, this number is supposed to be, this sequence is supposed to represent a number that is an upper bound for all of S. So we should just be able to take some random number in S and use that to find a lower bound for our sequence. So let's try it. So little s is going to be a random number in our set S, and it's going to be represented by some Cauchy sequence, and we'll call it S1, S2, S3, etc. So one of the things we know about xn, and this is from how we constructed the sequence back in the class activities, it is an upper bound of the entire set big S, right? That means that xn as a real number is greater than or equal to little s. Okay? And that means one of two things, right? Either xn is actually equal to s, or there exists some natural number big N such that whenever you have m bigger than big N, then xn is greater than sm, right? That would be the case where xn is strictly greater than s. And that means in either case that xn is going to be greater than or equal to any number that is a lower bound of the SMs, right? Whether it's equal to s or whether it's greater than the terms after a certain point, if we find a lower bound for all the numbers in that sequence, then that would be a lower bound also for xn. That would be less than xn. However, we do know that the sequence Sm is Cauchy, which means that it's bounded above, but more importantly to us, bounded below. That means if you take any number that's a lower bound for Sm, which there are plenty of them, the xn is bigger than it for each n, and that means the sequence xn is going to be bounded by any of those lower bounds. So we know xn is bounded below, it's decreasing, it's a Cauchy sequence. That means our number x, which is represented by the sequence xn, is a real number. Okay, so now we get into the proof proper of showing that x is the supremum of s, now that we know it's an actual real number. We will need to prove two things, just the normal two things we have to prove when we prove something is a supremum. We have to show that x is an upper bound for s, and then we also have to show that any real number that is smaller than x is not an upper bound for s. So to prove that x is an upper bound, we're going to start with that one. We're going to assume that little s is a random real number in the set S, and that is represented by the Cauchy sequence Sn. And then we're going to prove that little s is less than or equal to x. So we know for each n in the natural numbers that xn is, as a real number, is going to be greater than or equal to s. And again, that is just how we constructed this sequence. Again, if you want to know why, go back to the activities. So xn is an upper bound for the entire set S, so it's certainly going to be greater than or equal to little s, which is an element of big S. And as before, either that means that xn is equal to s, or it's bigger than s, which means there exists some, I'm going to say, natural number big N sub n, because this big natural number depends on which xn that we're talking about. It's a different one for x1 than it is for x2, which is different than x3, etc. Such that for all m greater than this integer n sub little n, we have x sub n is greater than Sm. So we have one of those two things happening. That gives us two cases that we have to consider, so we'll consider them one at a time. Well, what happens if xn is actually equal to s? And this can certainly happen, right? S itself could be a rational number, and right, a real number that represents a rational number, and so that number can be equal to one of the xn's. So what if that happens? Well, we know that the sequence xm is decreasing, which means that if we have m greater than or equal to n, we have xm is less than or equal to xn. But remember, xm is an upper bound for the entire set S. That means xm, the one that is smaller than xn, has to be greater than or equal to s. And if we put all those, which remember, s is equal to xn. And so that means xm, s, and xn literally have to be the same number, right? So xm equals xn, which equals s for all m greater than or equal to n. But that means that the sequence converges to the number s, which means that x actually has to equal s. And if x equals s, then it is certainly greater than or equal to s, which is what we wanted to prove. So if one of the xn's happens to equal to s, all the other xn's after that also equal to s, and then that means the entire number x has to equal s. So that leaves us with the case where x is bigger than, where it's bigger than Sm. So just to remind you about what that means, it means that there's some n sub little n, a natural number, such that whenever you have m bigger than n sub little n, we have xn is greater than Sm. And I'm going to just concentrate on one of those values of m. I'm going to concentrate on when m is 1 bigger than that n sub little n. And I'll call that, we have one of those for each of little n, and that is Sn prime. And we'll call that Sn prime equal to S sub n sub little n plus 1, right? The one that comes right after that. So if that is the case, then we know that xn is bigger than S sub n prime. But we also know, since there's one of those for each value of n, and we're not changing the order of the terms around, that Sn prime is a subsequence of the Sn. Now, the relation between subsequences and sequences, when we're talking about representing real numbers, we had a problem about that back when you were first looking at the equivalence relation. When you're doing equivalence relation, equivalence class exercises, you proved that if a real number was represented by a Cauchy sequence Rn, it was also represented by all of Rn's subsequences. And if we apply that to our situation here, that means that the number s is represented by that subsequence Sn prime of the original sequence. So what we have is s is equal to the real number represented by the Sn primes. We also know that xn is greater than Sn prime for all n greater than or equal to 1, not just after a certain point, but for all of them. And what that means is that by the definition of our order relation, either x is greater than s, or there's a slight possibility that x could be equal to s, but there is zero possibility that x could be less than s. And that proves that x is an upper bound for s, even in this case. Right, so that means we are done with our upper bound, the upper bound part of our proof. All we have to show is that x is the supremum by showing that anything smaller is not going to be an upper bound. And that's the next part, right? So, last issue. Suppose that we have some number y that is represented by some Cauchy sequence yn, so it's a real number, and we're going to assume that y is less than x. We want to show that y cannot possibly be an upper bound of s. Okay, and we're going to do that by contradiction, which means we're going to assume that y is an upper bound for s. And then I want you to recall that from the way we constructed our sequence for x, that for all the xn's, xn minus 1 over n is not an upper bound of s. So before we were really focused in on the fact that each xn was an upper bound of s. Now we're going to focus in on the fact that xn minus a little teeny tiny number is not an upper bound. And that means there is, for each of those n's, there is some element of s, we'll call it little s again, such that xn minus 1 over n is less than s. However, remember that we are assuming that y is an upper bound of s. That means s has to be less than or equal to y. And if we put those two inequalities together, that tells us that xn minus 1 over n also has to be less than y. So that's kind of nice. And when I say xn minus 1 over n, again, I'm thinking of it as a real number because y is a real number. So I'm thinking of it as being represented by the constant sequence that all the terms are xn minus 1 over n. Right, so just want to be clear about that. So we know that xn minus 1 over n is less than y. That means, by the definition of what it means by less than, right, we again have some n sub little n natural number, a different one for each value of n, right, potentially anyway, such that for all m greater than that n sub little n, we have x of n minus 1 over n is less than ym. So at some point in that sequence that represents y, the xn minus 1 over n is going to be smaller than those terms. And once again, I'm going to focus on one of those values of m. And again, just the one that's right after that little n sub little n. So n sub little n plus 1. So that's, I'm going to call it yn prime. And then what we get is that xn minus 1 over n is less than yn prime. And yn prime is a subsequence of yn. So once again, y can be represented by that subsequence yn prime. All right, so now we get to use the fact that y is less than x. We haven't actually used that fact. Right now, all we've used is our contradiction assumption that y is an upper bound of s. So by the definition of our order relation, there exists some, actually just part of the definition, not all of it, right? There exists some big N, a natural number, such that for all little n bigger than big N, we have yn prime less than xn. Right? So now we're just going to be concentrating on terms past that big N. We now have, for all little n greater than big N, well, we're going to put all of our inequalities together, right? We had, from the last slide, we had xn minus 1 over n less than yn prime. But now, from just a couple lines above, we have that yn prime is less than xn. And if we put those two together, we have a nice little sequence of inequalities. And if we were to subtract xn from all sides of those inequalities, we get negative 1 over n is less than yn prime minus xn is less than 0. And that should look a little bit suspicious to you, right? That looks like we're looking for something about the sequence yn prime minus xn, maybe using the equivalence relation. All right, answer is yes. So if we look at that in terms of like absolute, in terms of our squeeze theorem, right? We have a sequence on the left, negative 1 over n, that's heading to 0. On the right, we have a nice little constant sequence, just plain old 0, heading to 0. And that means by the squeeze theorem, the sequence yn prime minus xn converges to 0. But remember, that is exactly the condition for the two Cauchy sequences, xn and yn prime, to be equivalent, which means they represent the same real number, and that tells us that y equals x. But remember, we were assuming that y is strictly less than x, and that is a contradiction. That means that we finally proved that x was equal to the supremum of s, and s was any set that was bounded above. And we finally had the following theorem, which we've been waiting for a long time. The number system R satisfies the completeness axiom. Yay for us. All right, so if you haven't finished the activities for completeness axiom, go ahead and try the link for this video. You can look at the sequence xn's that if you haven't looked at those yet. And the second problem has to do with proving that there aren't any significantly different number systems that satisfy the real number axioms.